In this work, we design a regularizer that attains better generalization performance in federated learning. Federated learning is a machine learning paradigm that enables edge devices to collaboratively train a shared model while keeping all the training data on the device. This decoupling the ability to do machine learning from the need to store the data in the cloud. It's a privacy preserving model training in a distributed setting. It leverages the diversity of the data across the clients to train more robust and generalized model. So typical scenario in federated learning where we perform federated averaging. Each client perform local updates and share the model with the server. Server then aggregates and broadcasts again. So this process is repeated till convergence. In practice, the data is often heterogeneous. That heterogeneity can come from due to the quantity, and the label distribution can be different across the clients, and due to the feature imbalance. Features themselves can be different. And due to this heterogeneity, each client has its own local objective, which is very different from the others. So their own minimum can be different from each of the other clients. So due to this, each client starts drifting towards its own local minimum, a phenomenon called as client drift. So this is highly undesirable, as the goal of FL is to converge to a global model that generalizes well across all the clients. Along with the performance, communication cost is also very important in FL. So lower communication costs are preferred. Some attempts to solve this issue are decreasing the local steps, gradient correction, and regularization based methods. In centralized settings, it is well studied that converging to a flat minima improves the generalization performance. Sharpness aware minimizing techniques have been proposed to converge to a flat minima in centralized setting. So it has also been observed that global model trained in a federated fashion often converges to sharp minima, and this effect is exaggerated when there is data heterogeneity. To solve this, SAM has been later employed to FL settings in the work such as FedSAM. So motivated by these findings, we directly aim to minimize the top eigenvalue and attain flatness by designing the novel regularizer. So top eigenvalue is an indicator of flatness. So limitations of existing methods, SAM-based methods often require SAM-based methods require one extra forward and backward step. Since FL is performed on edge devices, it is important to have computationally efficient solutions. SAM-based methods assume the local model flatness leads to global model flatness. So we overcome these problems by proposing a novel flatness-inducing regularizer, which has lower computation, and we also theoretically show that local flatness indeed provides global flatness. So this is a typical FL formulation where we minimize the loss, overall loss, which is the average of all the client's losses. Now each client's loss is its own local loss averaged across the dataset. With the flatness constraints, we want to minimize the same loss, but with an additional constraint, the top eigenvalue of the Hessian of the global loss should be lower. So we translate this above objective to a penalized loss as in the equation 5. We now simplify the Hessian of the overall loss to the each client's Hessian. So the top eigenvalue can be upper bounded from equation 6 to equation 7, and using equation 7 we can upper bound the loss of the equation 5 with the equation 8. So we minimize this equation 8 as it is decomposed at client level, the task specific loss, which is LK, and the Hessian of the top eigenvalue of the Hessian of the client's loss. Now, in the works of Ravi Shankar et al., it has been empirically studied that evolution of the top eigenvalue of the overall Hessian and Layerwise Hessian is correlated. So computing the top eigenvalue of the overall Hessian is computationally intense. So instead we compute the top eigenvalue of the Layerwise Hessian. So we prove the following result where we bound the top eigenvalue of the Hessian with the Layerwise top eigenvalues. So we show that in this result, all the eigenvalues of the Hessian lie within this range, where this range is a function of the layer-wise Hessian top eigenvalue. Thus, we minimize the top eigenvalue of the layer-wise Hessian instead the overall Hessian top eigenvalue. Now, minimizing the layer-wise Hessian top eigenvalue is still a computationally challenging problem. So we further simplify by upper bounding the layer-wise top eigenvalue with the activation norms with the following results. So we show the result for fully connected layer. Similar results also hold for convolution layers as well. So in this figure, the first figure A shows the loss topology after convergence of the global model. As we can see, this topology is sharp. When we use the activation norm regularizer and train the model using federated averaging, we can see that loss becomes flat. So we compute the activation norm for each layer and we minimize that along with the task specific loss as shown in equation 9. LK is the task specific loss, which is cross entropy loss, and this is activation norm loss. So this activation norm loss is computed by averaging across the layers. And each layer activation norm is defined in equation 11 for con layers and equation 12 for fully connected layers. So experiments, we perform experiments on CIFAR 10, CIFAR 100 and tiny ImageNet data sets. And we consider 100 clients and 10% of them participate on an average per FL round. Data is distributed in a non-ID fashion based on the label imbalance created by sampling from Dirichlet distribution. We consider 500 communication rounds. We now present the accuracy communication cost results for CIFAR 100 and tiny ImageNet data set. We compute the number of rounds required to attain 50% accuracy for CIFAR 100 and 28% accuracy for tiny ImageNet. So as we can see, whenever minimizing the activation norm regularizer, man regularizer is applied to any of the algorithm, we can see significant boost in the performance. And also the communication rounds required to achieve the specified target. For example, CIFAR 100, 50% accuracy, we can consider like FedDyn if it requires 500 rounds to attain 50% accuracy. FedDyn plus man requires only 145 rounds. So this figure shows how the training progress is happening across the communication rounds. We plot the test accuracy versus the communication rounds. As here also we can see that whenever we augment any algorithm with the activation norm loss, man loss, and we can see a significant jump in the performance. For example, Fed average and can be jumped, performance can be improved to from blue to orange curve. So delta 0.3 represents the degree of heterogeneity. 0.3 means high heterogeneity, and 0.6 is moderate, and IID, we don't have any label heterogeneity. Same results we show for tiny ImageNet as well. Empirical Hessian analysis. In this analysis, we compute the top eigenvalue and trace of the Hessian of the global model. Here also we can see whenever we augment the minimizing activation norm loss, the top eigenvalue is reduced and trace is also reduced across the different data distributions. So in conclusion, we have theoretically shown that global flatness can be achieved by local flatness. We further approximated the local flatness by layer-wise Hessian eigenvalues, which in turn can be upper bounded by the activation norms. We have shown that the regularizer can be combined with the state-of-the-art methods to obtain significant performance and establish the new state-of-the-art. We have also shown that regularizer is computationally efficient because it involves only the computation of the activation norm.